experiment, we need to design what is the desired resultant compound that we want. Okay, let's say I want to get compound A. Then in order to get compound A, I have to go through some chemical reaction. I will need like use the DEF to have the synthesis and have the chemical reaction, then I will produce compound A. Why I get a compound A in solution, in water, in solution, then I crystallize it, I let it evaporate, then it become crystal. When it becomes crystal, I put it into the machine and use the X-ray to bombard it, and then I connect a diffraction pattern. Okay, from the diffraction pattern, I produce the structure. Okay, then the structure look like this. Okay, this is the structure of one basic. Okay, you can see that bending ring. This is bending ring. This is the N. This is the N. Sodium, nitrogen, and this is N. This is also N, and then we also have this part. Okay, so this is a basic. So this is a real picture. Okay, real picture means that you can see that all the ellipsoid are different. Okay, one basic, but when we combine many basics, then it become like this backing. Okay, backing. So of course in here we show a very small atom lah, because we want to make it clear. But in the real case, in one unit cell, this is one unit cell. Okay, remember that in chapter 4, the one unit cell that I introduced you just like this, that it only have one atom, a corner atom equivalent to one atom, right? But in the real case, like this organic compound, you can see that this is just one unit cell and there are maybe 100 to 1,000 atoms in one unit cell. Okay, that's also the reason why in chapter 4 I call them simple structure, because in the reality we are dealing with a lot of the atom instead of just one, two for PCC, four for face center cubic. But in the real case, you can see that there are many. Okay, so you can see that there are some empty space. So we also can calculate the packing fraction for this case lah, but it's much more complicated than what you have calculated in your chapter 2 lah. Okay, so we also have the X-ray powder diffraction. For X-ray powder diffraction, we don't record the 2D image. We record only one line image. Okay, so this one line, so we get the intensity. I believe some of your FYP project will require to use this SRPD, X-ray powder diffraction. For those who are working in nano lab, okay, you will require this knowledge to analyze the X-ray powder diffraction pattern. So basically, X-ray crystallography is just the X-ray interact with the crystal. So this is the structure of the crystal, the picture of crystal. Then this is X-ray tube. X-ray hit the crystal, produce the diffraction pattern. Okay, then the diffraction pattern, we convert it into the digital. Then we use a computer to do the calculation and compilation. Then, I mean, of course, it involves the refinement and some radial refinement, like what they call it, the porous synthesis, and so forth and so on. Then we obtain the structure like this. Okay. So in short, for X-ray crystallography, we don't take the real image, but then we take the diffraction pattern. The refraction pattern basically tell you the reciprocal space instead of real space. Okay, so from this reciprocal space, we go through the mathematic way like porous synthesis, then only we convert back it to the real space. So in short, for light microscope, we have the real space of the sample, and then we use the visible light, then we get the real space image. Very simple. But then for X-ray diffraction method, you have the real space sample, and then we use the X-ray to shoot it on it. We got a diffraction pattern. Diffraction pattern, this one. And diffraction pattern is actually in the reciprocal lattice. Okay, not the real one. And in next chapter and next two chapters, I will explain what is reciprocal lattice. Okay, so by converting it to the reciprocal lattice, not converted, but we obtain the diffraction pattern. Then the diffraction pattern actually representing the reciprocal lattice. So from this reciprocal lattice, we want to get the real space image, right? So we have to put it into the computer and then go through some forest analysis. Then only you will get the real space image. Okay, so the difference between the light microscope and the X-ray diffraction is that for light microscope, it's just real space, real lattice, but then for the X-ray crystallography is you have to go through the reciprocal space, then convert it back to the real space by using a very complicated mathematical way. Okay, then now I will proceed with the diffraction. So diffraction by crystal. Diffraction will provide the information on the position of atom in the crystal. And then the diffraction occurs when the wavelength lambda of the source used has a value smaller or equivalent to the distance between the atom, which is around 1 angstrom. And there are a few sources that we can use, like neutron, electron, and X-ray. Okay, so this is a molecule. When you put the molecule into the unit cell is the smallest repetitive component, and then when we have many smallest repetitive component, the unit cell, when you stack them together, then you get the crystal structure. And then this is the structure for the protein. So if you are interested to know what is the structure of the protein, DNA, and so on and so on, you can go online and you just type the protein crystal structure. Then you will see a lot of structure, and the number of the atom inside one unit cell is extremely many. Okay. So there are a few sources that we can use. The first one is the X-ray. The second one is the neutron. And then the third one is the electron. Okay, so I will start from the X-ray. For photon in X-ray, we know that we can get the wavelength of the X-ray by using this equation. We know that lambda equal to C over nu equal to hc over E, right? So H is a constant, C is a constant. So when you substitute H here, substitute C here, C is the speed of light, H is the Planck constant. So these two are constant, then you substitute E, you will get 12.4. So both of them are constant, so it's a fixed value of 12.4. Then E is the energy that you apply. So let's say if you want to get the wavelength of the X-ray is about 1 angstrom, then you need to apply the energy also relatively comparable to 12.4 kilo electron volt. So that 12.4 over 12.4 you get 1 angstrom. Okay, so you can control the wavelength of the X-ray by controlling the energy that you apply to the X-ray source. For X-ray crystal diffraction, the energy is normally used between 10 to 50 kilo electron volt. Okay, so 10 to 50 kilo electron volt.